All right, we'll get this show on the road. One of the things I'll tell you is that this review is probably going to be a tad shorter than the statics review that I did a couple of weeks ago. This is, I believe, a critical topic on the exam because it does show up in other areas. Understanding stress computation is important in things like soils. It's important in structural mechanics. You see this in steel and concrete. You see it in a lot of subsequent areas, and it's usually a pretty sizable thing on the exam. And here's the thing that I want to address right off the bat. This is not hard, okay? It's not. I think that a lot of times students, not just at Marshall, but at other institutions, tend to treat mechanics of deformable bodies as one of the more difficult courses that they've had, or they didn't learn anything or whatever, and they're just like, that's a pass. But by and large, a lot of the stuff that's in mechanics and materials is very doable, and it borrows off of a lot of other stuff that you've done in other courses, namely statics and some pretty basic formulas and equations. One thing I will say about mechanics and materials right off the bat is that I do think that mechanics of materials is a topic on the exam that is incredibly sensitive to unit conversions, okay? So this is something that I would sort of figure out right at the beginning in terms of a consistent unit system, a consistent way of doing things. I'm going to disconnect this keyboard here. One of the things I'll mention right off the bat is, so I'm actually teaching mechanics of deformable bodies this semester, and one of the things that I did right before the first exam, because we just had our first exam in there not too long ago, is I sort of developed what I called Dr. Mike's preferred unit system. And I gave them some advice on what I thought would be a good way of going about things on the exam. And I do think that this translates to the FE exam pretty well. Now, the thing about mechanics and materials and the thing about the FE exam, and this translates into concrete design and steel design and other topics, is that you could get stuff in both US units as well as SI, okay? So here's sort of my preferred unit system right off the bat, okay? So I'm actually starting right off the bat with Dr. Mike's preferred units. Okay, so we're going to have two different systems. So we're going to have USCS units and we're going to have SI. Okay, now in both of these unit systems, we're going to have to establish what are called force units and length units. If you've ever done any type of finite element modeling using any advanced software and whatnot, a lot of times you'll find that those software programs are unitless by nature, and you kind of have to establish this right off the bat. And I think in mechanics of materials, you kind of need to start right off the bat, and I think that this can serve to reduce errors moving forward. It's not always necessary, but I would argue that if there's ever a situation where you're going to see the need to do a lot of conversions, I would convert to a consistent unit system. For US units, what I like to do is I like to express all my forces in kips and all of my lengths in inches, okay? The reason why is because it is sort of manageable to figure out what other related terms need to be in. So for example, Young's modulus. The Young's modulus for steel. What is the Young's modulus for steel? 29,000 what? There we go. Right off the bat, kips and square inches, okay? For example, if we have a moment of inertia, we typically express those in inches to the fourth, okay? But there are other instances where you kind of need to pay attention. So for example, if you're looking at the length of a member, the length of the members, let's say how long is the beam in this building, is typically going to be expressed in feet, right? So what that means is that you're going to need to convert that right off the bat to inches, okay? The reason why I've sort of chosen this base unit system is because I believe that the resulting necessary conversions are among the simplest to do, okay? If there's any one area where maybe the conversions get a little tricky and you just kind of have to pay attention is with things like moments or torques, because they need to be expressed in inch kips, okay? If you get that, sort of the units work themselves out, okay? And that tends to be a good unit system for US units. For SI, what I tend to like for SI is forces in kilonewtons and lengths in millimeters, okay? So the reason why, so there's a couple reasons why. First off, if you look at moments and torques, so a lot of times they will be expressed in Newton meters, but did you know that a Newton meter equals a kilonewton millimeter? That they're the exact same? Because you've got K 10 to the third, M 10 to the negative third, so they cancel each other out. So it's very easy to do that unit conversion. And whenever you're dealing in stresses, which is going to be kilonewtons per meters or millimeters squared, a Newton over a meter squared is a Pascal, right? So if you're dealing with kilonewtons and millimeters squared, we need we need to know what that equals in SI. And in SI, kilonewtons over millimeters squared is gigapascals, okay? Because we have kilonewtons, 10 to the third, and then we're dividing by 10 to the minus 3, but then it's squared, so it's 10 to the third and 10 to the 6, so you get 10 to the 9th. So that's where you get the giga. So in SI, what ends up happening is your stresses might be a little small, but every one of the other unit conversions tends to work out pretty well. You did tend to get pretty high moments of inertia and what have you, so you kind of need to be aware of that. But by and large, I think these are the most usable unit systems in the science. And again, this is, I think, honestly, what trips a lot of students up. The ideas are pretty simple. I do not want to see any student taking the FE exam have a problem with units. It's like, come on, we should be able to work out a consistent unit system. And I think of any of the topics on the exam, this is the one that's trickiest in regards to units. So this is sort of the when in doubt, convert everything to this, okay? Any questions before we move on? All right. So this is going to be a two-part lecture in the world of mechanics of deformable bodies. And so we're going to start with what is essentially the first half of Engineering 216, okay? And so what I am focused on is basically everything that I cover on Exam 1 and a good chunk of what we do on Exam 2. When we come back on Thursday, we'll finish out Exam 2. We'll talk about Moore's circle and principal stresses, and if we have time, we'll get into some buckling stuff. Although, if you've had me for steel design, which I think everybody in here has, except for you who are taking it now, what we do in there with buckling, you're good. If you remember Euler buckling, like pi squared E, KL over R squared, if you remember all that, it's the same concept in Engineering 216. In fact, we do more in steel design than we did in there. So, you know, I really want to, the Moore's circle stuff is kind of what I want to focus on, because I think that students think that Moore's circle is one of the zaniest ideas out there, and it's actually really easy. I sometimes think it's not explained well, so I want to try and give it its justice, if you will, starting on Thursday. Okay, let's talk about axially loaded members. So just so you're aware, we're going to do axially loaded members, and then we're going to do torsion, okay? And those two topics seem like they are incredibly unrelated, because how could yanking on a member and twisting a member, how could they be aligned? Well, they're actually very similar in terms of the theory, in terms of the math that's performed, in terms of the calculations that you do, and so on and so forth, because both of the forces are along the axis in the direction of the axis. It's just one's a force and one's a moment. What we're going to do here is talk about some of the base formulas, and I'll bring up the FE reference manual here in a second. Do you have a question? Oh, okay. No, if you do, don't hesitate. All right. So the initial topic in a mechanics and materials course is to take an element and yank on it, or take an element and compress it. We're talking about axial loads, either stretch or compress. Now, one of the tenets in mechanics and materials is that everything in this universe is deformable. You apply load, it results in deformation. We don't have any vibraniums or adamantiums or anything in the real world. So everything will experience deformation. And what we tend to do is we tend to connect that from one end, applied load, to resulting deformation at the other end. And we have a couple steps in between. So the first thing that we try and do is, okay, we say, if I have applied load, I'm going to say I have this member, it's subjected to 20 kips. What I am then going to do is try and normalize that applied force. And the way that I do that is I introduce a term called stress, okay? Now, whenever I'm first teaching the concept of stress, I say think pressure, because stress and pressure have a lot of similarities in terms of their units and how they're computed, etc. The difference between stresses and pressures, and why solid mechanics folks deal with pressures deal with stresses, is because pressures are more for fluids. Pressures are more for liquids and gases. Solids, on the other hand, experience stresses. So that's kind of the difference. If you're ever wondering what's the difference between stress and pressure, it's that stress is more with solid objects and pressures are for liquids and gases. So whenever I have an object and I'm yanking on it, it's going to deform. Stress is one of the tools that helps remove the geometry from the problem. So what do I mean by removing the geometry? If I have this eraser here, and I take this eraser and I compress it with some force P, if I push on it, I propose that it deforms. Now, what's the volume of this eraser? The volume is the cross-sectional area times the length, right? Stress is one of the ways that I can remove the geometry from the problem by dividing out the effects of area. Strain is the way that I divide out the effects of length. So if stress is a normalized expression of applied load, then strain is a normalized expression of resulting deformation, okay? The reason why those are valuable is because it allows us to look at objects from a material perspective. It's not the amount of force, it's the force per unit length, okay? It's not the deformation, the force per unit area. It's not the deformation, it's the deformation per unit length, okay? The reason why that's valuable is it allows us to look at engineering systems from apples to apples, okay? I am physically strong enough that I could grab that Coke can, assuming it's empty because I don't want to make a mess, and I could crush it pretty easily with my bare hands, just as everybody in here could with their respective soda cans. But could you do that if it was a solid billet of aluminum? Of course not, you know. I mean, we're not, you know, the Avengers or anything. But what makes the solid billet of aluminum stronger, if you will, than the soda can is a change in geometry. If it was the same material, it would fail under the same stress and result in the same strain. But simply because the solid billet of aluminum is bigger, it's just going to take more load to reach that same level of stress. Does that make sense? Okay, so that's what stress and strain allow us to do. They allow us to remove the geometry from the problem so I can look at the solid billet of aluminum and the empty soda can in the same light, okay? Now, one of the things that we do to classify materials, and it is arguably the baseline, simplest, square one means of classifying material, is we take a piece of material and we yank on it and we apply load until it fails, okay? And by dividing out the effects of area and length, we can generate what's called a stress-strain curve. So this is a representation of the stress-strain curve of carbon steel. We tend to use carbon steel as a means of introducing the concepts of stress and strain and their relationships, because carbon steel is a material that you can sort of set your watch by in terms of its properties. They haven't changed in a very long time, and they're certainly not going to change anytime soon. They're solid in terms of their performance. If I go do a tensile test today on a piece of carbon steel, I will get essentially the same representative plot. Now, what we tend to do in most engineering applications is we tend to restrict our behavior towards this linear region. The reason why is because in that region, steel and many engineering materials exhibit this behavior, have what's called elastic response. And what elastic behavior means is that if I apply load, it deforms, but if I let it go, it snaps back to its original shape, just like a rubber band. If I take a rubber band and I stretch it, it deforms. Let it go, it snaps back to its original condition. And more often than not, we prefer that in our engineering systems because we don't really like permanent deformation. Sometimes permanent deformations are unavoidable. There are a couple instances where they're actually desired, but more often than not, we tend to avoid or not like permanent deformation. So we tend to operate in most of our engineering principles in the linear range, okay? Now the slope of this linear portion of the stress-strain curve is what's called the elastic modulus, or Young's modulus. So a lot of times in engineering problems, we have a means of connecting the load to the stress, and that's something like sigma equals P over A. We have a means of connecting the strain to the deformation, the change in length over the original length. But if we restrict our behavior to the linear range, then we can relate stress and strain through a material property such as Young's modulus. The Young's modulus for steel, as we said, is 29,000 KSI. That's one of the reasons why that number is so important, because if your stresses are linear and elastic, you can relate applied load to resulting deformation very easily. So instead of stress, I'll put P over A. Instead of strain, delta over L, rearrange, and boom. I get the axial deformation of a rod as PL over EA. I'm going to write that formula down here on the board. It's right here highlighted in yellow, but I'm doing that because I want to make a point about torsion here in a little bit, and why torsion is a natural extension past axial members. Like, you do axial members, and then torsion comes next, and there's a very good reason why. Okay, a couple of other items that I think are worth mentioning. The first is what's called the Poisson Effect. I'm sure you all sitting here listening to me, as well as people who are going to watch this video in the future, are going to go, Dr. Mike, this little animation's been going on for the past 15 minutes. You've been rambling on. What the hell is going on with that thing? Okay, so this is a representation of what's called the Poisson Effect. And so what the Poisson Effect basically means is, if I take an element and I yank on it, not only is it going to get longer, but it's going to get thinner, okay? And the Poisson's ratio, this Greek letter nu, tells us the relationship between lateral strain and longitudinal strain. That parameter, Poisson's ratio, is kind of important. You can take E and Poisson's ratio and use those together to compute the shear modulus, and it tends to show up a lot in various places in engineering computation. So for instance, for steel, the Poisson's ratio is about 0.3. That's usually what we tend to use as a default. And Poisson's ratios tend to hover around that 0.2, 0.3 range, sometimes a little smaller, sometimes a little bigger. Finally, and I hope by now that you kind of understand the concept of a factor of safety, that there is a difference between the allowable stress and how much we're actually applying. This is arguably much simpler than what we do in steel design with LRFD or anything like that. What we're talking about is basic. The allowable stress is 50 KSI, but if I use a factor of safety of 2, I'm going to restrict that stress to 25 KSI. Just cut the allowable stress by the factor of whatever your factor of safety is. You might have problems that ask you to compute the resulting factor of safety. So you compute the stresses. It says sigma allowable is 26 KSI. Divide the 2 to get your factor of safety. Or you have to account for it. And whether you use your factor of safety to bump up the applied load or reduce the allowable stress, it has the same effect, okay? Does that make sense? All right. Now, in this crazy lecture, I only have 3 problems, but these 3 problems are a little involved. They are intended to explore the concepts, if you will, to get our brains thinking a little bit about on mechanics and materials to explore all of the units situations we've been talking about. So a lot going on here, but I think it's a pretty valuable exercise. Okay, so this is example one. Let's see if we can digest what's going on here in this example. I'm going to go to my notebook here. Let me make that bigger. And I'll give you all a sec to write this down. But I have a 10 kilogram axial load that is uniformly carried by an aluminum pipe. The aluminum pipe has an outside diameter of 10 centimeters and an inside diameter of 9.6 centimeters. Okay? The pipe is 1.2 meters long. Young's modulus for the aluminum alloy is 75,000 megapascals. Neglecting the effects of buckling, and again, we'll probably talk about buckling a little bit later, but neglecting the effects of buckling, how much is the pipe compressed? So this is a perfect example of a delta equals PL over EA problem. We have the applied load, the member length, the E, and the cross-sectional area. And so really all you need is if you can compute those four quantities and get them into the appropriate units, plug and chug, okay? The other thing I really love about this problem is what if I told you, what if I said, what is the stress? Well, the stress is just P over A. So if you can compute that, you can certainly compute the stress. What if I asked you what the strain was? Well, if you have the deflection over L, there's the strain. So you can determine everything that you need between applied load and resulting deformation with just this one set of data. It's really not that hard. So what I want to do is I want to take each one of these terms one by one and see if we can address them. Now, what I'm going to do is I'm going to explore this, this unit system I mentioned earlier. Hold on. Okay. Force equals kilonewtons and length equals millimeters. Okay? So up here on the top, I want to figure out so if this is our formula, what do these terms need to be in? Okay? So P is our applied load, that's the force, that needs to be in kilonewtons. L needs to be, in this case, the length in millimeters. E needs to be in gigapascals, and A needs to be in millimeters squared. So it gives us some guidance on how to do our appropriate unit conversion. So we're just going to take each of these terms one at a time, see what we need to do. Now, let's first start off with the applied load. So I have a 10 kilogram axial load uniformly carried by aluminum pipe. What's the problem there?
That's a mass.
That's a mass. And so if we're talking about a pipe supporting a mass, what do I need to do to convert that to a force? And that acceleration would be? There you go. 10 kilograms. And so that's going to be 98.1 newtons. So (0.0981 kilonewtons. I do that right? 1, 2, 3. Yep. So far, so good? Length is going to be what? The pipe is 1.2 meters long or 1,200 millimeters long. Okay? E is the Young's modulus. E is given as 75,000 megapascals. Now, how am I going to convert that to gigapascals? Exactly, yes. Because giga is a bigger unit. So like think about a flash drive, right? 4,000 megabytes is sort of like 4 gigabytes, right? So we're going to divide. So that's going to be 75 gigapascals. Now, the area takes a little bit of discussion, so let's see if we can figure out what's going on with the area. So I have a pipe. Okay? Now, the inside diameter of that pipe is 9.6 centimeters or 96 millimeters, right? So that's me converting that to millimeters by just multiplying by 10. The outside diameter is 100 millimeters. Now, how do you determine the area of a circle? Now, the area of a circle, I know the mathematicians would love me and say in pi r squared, right? But here's the thing, okay? And this is the difference between mathematicians and engineers. If I go to Lowe's and I buy pipe, what is it going to, how am I going to go to the customer service rep at Lowe's and say, I need a pipe with a 3.75 inch radius? No. How are pipes expressed? In diameter. How are bolts expressed? Diameter. That's just how terms are expressed. And so understanding how to compute area in terms of diameter will save you time, especially on an exam like this. So if given the diameter of a circle, the area is pi d squared over 4, right? Now we have a pipe, okay? How do I compute the area of a pipe, okay? Well, we're talking about this shaded region right here. So how do I compute the area of that shaded region? I take the area of the big circle and I subtract from that the area of the small circle. So in this case, area is pi over 4, we'll call it the outer diameter squared, minus pi over 4 times the inner diameter squared. Or if you want to save yourself some time, we can do that. So what do we get from our Casio FX115 ES Plus or similar scientific calculator?
I got 615.8 millimeters here.
Do I have a second on that? So here's our formula. Delta equals PL over EA. What do we get?
2.55 times 10 to the negative 3rd millimeters.
Boom. What do you think? So here's the point about this problem. All right? These 4 quantities, were they that hard to deal with? Were they that hard to compute? What if I asked you for the stress? The stress is just this over that. Boom. What if I asked you for the strain? this over the length, you know? It's not that hard, you know? I don't want mechanics of materials to seem like this scary topic on the exam, because it's really not. Okay? Let me show you something else. Just so you are aware, this is the NCEES reference manual. I think this is the most recent one, although it might not be. Might be a little old. But mechanics of materials, here's the section in the manual related to that. This is the stress strain curve for mild steel. This is the same one that I was looking at before. It's just zoomed in a little far for so you can see the linear region and whatnot. But if you look, here's our definitions for strain. Let me zoom out a little bit. Ooh, I'm zooming in too far. Sorry, I'm getting crazy with my mouse clicker and whatnot. Here's the definition for strain and percent elongation. We have uniaxial loading. Stress is P over A. Delta equals PL over A, or EA, whichever one you want to do. So everything that I'm talking about here is located in the manual, okay? In the manual, it's called Mechanics of Materials, not Mechanics of Deformable Bodies, but same idea. Questions? Are you feeling better about this already? Okay. All right. So then the question becomes, if that's the case, why torsion next? Why go from axial loads to torsion? Because they don't seem to be the same thing. Remember this formula here? This is the axial deformation in a bar. The angle of twist in a torsional shaft is computed as follows. Notice how those formulas look really similar? They are, and they're also, I mean, not only are they really similar, but let's look at the parameters. So we have up top a member length, a member length. What's the next term? This is applied load. This is applied torque. So some external force or demand being applied to the system. What's on the bottom? Here we have E, here we have G. Both of those are material properties. Now what about the other ones? A and J. Those are section properties. Now, what are section properties? Section properties are just fancy numbers that characterize a given shape. For instance, what are some numbers that I could use to characterize this rectangular cross-section? The area, that's a section property. The perimeter, that's a section property. The centroid, that's a section property. Those are just numbers that characterize this shape, and that's all a section property is. I propose that J is just a different section property. It is a section property that arises from the derivation of the governing expressions for torsion. Now, here's something that I want you to recognize on the FE exam. Unless I'm absurdly wrong on this, and if I was, I'd probably go buy a Powerball ticket. You will not have a problem on the exam involving torsion and a cross-section that is not circular, okay? Your torsion problems will either have a circular cross-section like a solid shaft or a pipe, okay? Now, there's a couple reasons for that. First off, real life. Go look at camshafts in cars and shafts between motors that are delivering torque to engineering systems and whatnot, and you will find that they are circular, okay? Circular cross-sections are the most efficient in resisting torsion. That's one reason. But another incredibly important reason is that circular cross-sections do not warp, okay? When you twist a circular cross-sections do not warp. When you twist a circular cross-section, it rotates. So you take the shaft, you twist it, and all it does is rotate. Non-circular cross-sections do not just rotate. They rotate and they also warp. They deform out of plane, okay? If I take this eraser and twist it, the ends of the eraser come in and out of the plane, and that's what's called warping. Circular cross-sections do not do that. For those of you that have had me for steel design, we've already had we had a discussion about warping when we talked about beams. Because when you have a beam and the top of it is experiencing compression and the bottom of it is experiencing tension, things in compression like to buckle, it doesn't know what to do. So it sort of kicks out and twists, and it undergoes this lateral torsional buckling mode, okay? Well, if you go into the governing equations governing that torsion, you find expressions related to warping, because that's where I-beams get their torsional strength, is from that warping effect. Under the pure torsion, they're incredibly weak, okay? So that's why if we didn't have torsion, if we didn't have warping effects in I-beams, we wouldn't be able to use I-beams for design at all. Like, they wouldn't work, okay? But circular cross-sections do not warp. They simply rotate, okay? So whenever you're on the FE exam, your torsion problems will be circular in nature. And if you get a question why, circular cross-sections don't warp, okay? So in order to determine the stress for a circular cross-section, we start to experience something that's a little new. And there is some things that are a little different from axial loads, and that is that the stresses change dependent upon where you look. So for example, if you take a member and you subject it to axial force, take this eraser and just press on it, and you get 10 KSI. It's 10 KSI everywhere. It's 10 KSI here, 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 here. It's a uniform stress across the board. However, with torsion and with things like bending, the stress changes depending upon where you look. And I think a lot of students really understand this with bending. You take an element, you bend it along the neutral axis, you get no strain or stress at all. You get compression one way, tension along the other way, right? You know, so you bend the beam, it's, you know, smiley face bending, it's compression on the top, tension on the bottom, zero bending stress and strain along the centroid. Torsion is where in mechanics and materials you first start learning about how stresses can change dependent upon where you look. If I take a circular element and I twist it, it rotates, it twists, right? So if I look at deformation, let's say before and after, let's say I draw a little point right here and I twist it, afterwards that point moves, right? And it has deformed. If I draw a dot right here, twist, it moves a little bit, right? But what about right here in the center? If I twist it, the center doesn't move, right? It rotates, but it doesn't move, right? Make sense? So I propose that from a stress standpoint, stress varies away from the center, okay? So one of the questions I ask a lot on my exams for Engineering 216 is I ask, if you have a torsional shaft and you have two materials, a really good material and a really crappy material, which material do you put in the middle? The good material or the crappy material? You put the crappy material in the middle, because you want the good material on the outside, because that's what's going to see all the biggest stresses, right? So, you know, for example, if you had a steel tube and maybe an aluminum shaft, you put the aluminum in the middle, because the aluminum can't carry as much load as the steel. Does that make sense? Now, the maximum shear stress, which is on the outside, is computed as T times the radius, how far you are from the center, divided by J. J is the torsional constant, and for circles, it's the polar moment of inertia. And the polar moment of inertia for a circle is pi d to the 4th over 32, or for a pipe, it's doing pi over 32, and it's sort of the same thing we did with the area, the outer diameter minus the inner diameter. You can do the J on the outside minus the J on the inside. So that's the maximum shear stress. The maximum shear strain is we just divide by G. Sometimes you may be given the G value, sometimes you have to compute it. If you have to compute it, We have a very simple relationship between E and the Poisson's ratio. We just take E divided by 2 times 1 plus Poisson's ratio. That'll give us the shear modulus. So if E is the relationship between applied normal stress and resulting normal strain, G is the ratio between applied shear stress and resulting shear strain. And shear strain is just the angle change that we get infinitesimally, if you will. Okay. Let me go back to the notebook here. All right, a steel pipe is fixed on one end and subjected to a torque of 100,000 Newton meters. The pipe is originally 3 meters in length with an outside diameter of 35 centimeters and a wall thickness of 1 centimeter. So we got to be careful about these dimensions here, because getting the inner diameter, this is an easy mistake on the FE exam, and I want to make sure that we're clear on this. Steel has a modulus of elasticity of 210 gigapascals. That is about 29,000 KSI, by the way. That's pretty close. And a Poisson's ratio of 0.3. What is the resulting angle of twist? So, like before, TL over GJ. Now, Dr. Mike's units. So, our torque is in Newton meters. What's the trick I told you about the torques? That Newton meters is the same as what?
Kilonewton millimeters.
Exactly. And if that's our base unit, we don't have to do anything with the torque. So the torque was given as 100,000 Newton meters, but that's the same as 100,000 kilonewton millimeters. Okay. Now the length needs to also be in millimeters. We were given the length of 3 meters. It's the G and the J that we need a little bit of work on. So let's look at the G. By the way, what units do we think G needs to be in at the end of the day? There you go. Which isn't going to be a problem. So for G, what we're going to do is use our relationship between E and Poisson's ratio. And again, that's in the manual, really easy to find. So what is that? Say it again.
150 gigapascals. Oh, it's plus?
Yes. Sorry, that's kind of small.
80.77 gigapascals.
Okay. I was going to say.
I was just trying to remember for the last slide because I forgot to write it down.
Yeah. Okay. All right. Now for J, we gotta draw our cross section out a little bit because again, I want to kind of make sure this makes sense. Now, first off, I'll go ahead and remind you of this formula here. J is pi over 32 d to the fourth, or J outer minus J inner. But we got to be careful on our computations, okay? So we were told in the problem that our outer diameter is 35 centimeters, or 350 millimeters, and we were given the wall thickness of 1 centimeter or 10 millimeters. What is DI? What's the inner diameter? So if I give you a 350 millimeter outer diameter and a wall thickness of 10 millimeters, what's the inner diameter?
330 millimeters.
330. Now how'd you get 330?
Because you have to subtract 2 of the difference between the diameters.
That's 100% right. We have the outer diameter. We got to come in one thickness and another thickness to get the inner diameter, right? That's really easy to just say, oh, it's 34. No, it's 33, right? Because we have to subtract 2 thicknesses. Does that make sense? So you have an outer diameter and an inner diameter, and if you want to get this dimension right here, you got to subtract 2 of those. You got to subtract that and that. Yes?
Is that why you used to write, I think it's 2, or have like a subscript of 2 before the T? That way, like, we know to multiply 2 times that for the thickness.
You could do that, but what I would argue, the only thing I would say is, for stuff like this, sometimes it's best to try and not memorize formulas. If you understand the ideas, then I think you'll find the mathematics are a little simpler. Here's the reason why I say that. So for number one, you're given an FE reference manual, right? And if you try and memorize a couple formulas here and there, I think you'll forget a lot of the other stuff on the manual or on the exam. So if that works for you, go for it. But I try and avoid the memorization stuff. There's a couple things that I think are worth memorizing, but I'll tell you this. So if there are any, let me just take a step back. If there are any 2 secrets that I think that are required to pass the exam, the first is understanding how that works, that little calculator. The statistics functions, the cross products, stuff like that, know how to use it. I think some testing centers will actually make you take the sleeve off. So know how to use that stuff. And the second, I'm just curious, and I'm not trying to pick on people, I'm curious, how many of you have actually downloaded the reference manual and reviewed it on your own? I'm asking.
We had to last semester.
You had to?
Yeah.
Good.
I went through part of your original review.
Okay, yeah.
I haven't done it yet. I haven't done it yet.
So get on your MyNCS account and download it, and actually look at it. See, here's the thing. I think that there is an assumption among students now that I don't need to do that because there's 2 little keys on the keyboard. One's called Control and one's called F. Now I can hit those 2 buttons and I just type in the words and it'll just tell me anything I need to know. But I think that there is some value in understanding what's in that book and, more importantly, what isn't in that book, okay? What's in the book, where it is, what it looks like. I mean, for example, I teach statics and I teach mechanics of deformable bodies. I took statics in the fall, mechanics of materials in the spring. The textbook that I used for both classes had very different formats on how to list the centroids, the moments of inertia, the stuff in the back, and I kind of like the mechanics of materials book better. I kind of think the statics textbook made it a little more complicated than it needed to be. But if you've never looked at that guide in the manual, which we're going to look at here in a little bit, you're like, man, I don't know what it's saying. I don't know the format. Take some time and look at it. It is an edge that you are not giving yourself when you're doing this. Okay. All right. So now for J. Oh, so this is 330. By the way, you are taking millimeters to the 4th, so J is a big number. It usually is. It's okay. Anybody have an answer for this? It's big.
3.09 times 10 to the 8th millimeters quadrupled.
Millimeters.
That's not even, that wouldn't even be quadrupled.
It's 2 to the 4th.
2 to the 4th.
Yeah.
Quadrupled is times 4.
Yeah. So a lot of times I think students, so let me say a couple of things about that, because I think a lot of times students think this is like the 4th dimension and we're over in quantum mechanics land. That's not really what's going on. So what we're basically doing here is if I have an area, right, the moment of that area would be area times moment arm. And so that would be in millimeters to the 3rd. This is just a second moment of area, okay? So it's not, we're not getting into the 4th dimension. Let me give you another example of where engineers have resolved this in another light. The moment of inertia of a beam is also listed in inches to the 4th, but there is an incredibly convenient way of expressing that, and that's through a radius of gyration. So what do we do with the radius of gyration? We take a moment of inertia, we divide it by the area, and we take the square root. You know those L over R values that we looked up in steel design? What do you think R is? R is just the moment of inertia divided by the area, take the square root. So R is basically the same as I, it's just normalized a little bit. And so that if you compute L over R, you get a unitless quantity. And L over R, as we know, has very important applications in the world of mechanics. It is an expression of slenderness. In steel design, we have limits on tension member slenderness, and in compression member land, the larger the slenderness, the lower the buckling capacity. Remember that? So that's coming later in steel design, and we may talk about that on Thursday should we have time. Make sense? So yeah, don't think that it's a little, don't think that we're getting into the 4th dimension. Warping constants are inches to the 6th, so, but it's not, we're in the 6th dimension or anything. Okay, so now we've got the angle of twist as TLGJ. So I think this was 100,000 kilonewton millimeter. Now what's interesting is the units for an angle of twist. So if you look on top, you have kilonewtons times millimeters squared. And on the bottom, you have millimeters to the 4th, and then kilonewtons over millimeters squared. So if you follow it through, all the units cancel. So we are getting an angle of twist that is unitless. In mathematics, when you have an angle that doesn't have any units expressed next to it, what is that angle measured in? Radians. So whatever value we get, this is going to be in radians. And what do we get? That? There, yeah, okay. Let me stop for a sec and see if anybody has any questions. Are you feeling a little better? By the way, these problems are, I would say, more involved than what you get on the exam. I think there's more to it, if you ask me. I'm also taking my time going through it. I think this is a little bit more involved than what you get on the exam, but I think if you were to just do the problem instead of me just yakking on about it, I think it would go faster. So, what do you think? All right. Now, I want to close. Yes.
I have a question that I think may relate more to the previous content that we were just looking at. But the average, so the average strain is equal to, well, the average strain, so deformation is equal to the Young's modulus times the average strain.
Yes.
Okay, so average strain, that means it's not necessarily axial or longitudinal. That just means the average strain. So
No. Okay. So if
we're
you're,
going to relate that to Poisson's ratio because which is accurate longitudinal.
all right. So let me that's fine, it's fine. So let me explain the meaning. That's a very good question. And let me explain the reasoning for the average term there. The reasoning for the average term there is what's called the St. Venant effect, or what I think would be easier for you to relate it to would be what happens in steel tension members under the presence of shear lag. So remember in steel design that you have a tension member and you've got bolts going through the member at a given end, right?
Is that U?
Remember the U factor, right?
Yeah.
Now, what was that for? That was for the fact that there at the connection, things are weird. The stresses are just, they're sort of wonky, right? But away from the tension member, away from that connection region, the stresses kind of even out, right? That average, if you will, is sort of looking at the average strain along the member, the average stress along the member. It is ignoring stress concentration effects that you might get at the end. I think from a mechanics of materials perspective, there's probably not a lot of need to discuss that with you today because it's not something typically that civil engineers have to deal with on the FE exam. We do have to deal with stress concentrations in various arenas like shear lag factors, but we have our own way of dealing with it. You start getting into the rabbit hole of how civil engineers and mechanical engineers actually do some things a little bit differently. So that's what they're talking about. But are they talking about axial stress and strain? Yes. But it's average along the cross section. Does that make sense? That's a really good question. Anybody else? This is good stuff. I like this. This is good stuff. Okay. Now I want to talk about bending. Okay. Bending in mechanics of material land is a little bit different in the sense that, so I'm currently teaching mechanics of materials right now. And with axial stresses, you can kind of jump right in. And with torsion, you can kind of jump right in. That's not really the case with bending, because what ends up happening with bending is the actual bending formula is really easy. It's just sigma equals my over I. The problem is you have to take a step back and go, okay, everybody, y'all remember how to draw a shear and moment diagram? Because you need that in order to get the M, right? Do you remember how to compute a moment of inertia? Because that's the I. So there's a lot of background calculations that you need to handle first. And then the actual sigma equals my over I is actually pretty easy, okay? So what do you need in order to properly handle bending stresses, okay? Well, first off, you need to be able to construct shear and moment diagrams in beams. You just have to. It is very typical in mechanics and materials problems related to bending that you are given a beam subjected to a point load or a distributed load or whatever. And the question is, what is the bending stress, the maximum bending stress due to said load? So you have to be able to compute support reactions and draw a shear diagram, draw a moment diagram, etc. Okay? So that's the moment. Okay? Now, in order to determine the bending stress is determined through the quantity sigma equals my over I. Okay? Now, M is whatever moment is applied to the cross-section, usually a maximum bending moment from a moment diagram, but they might say maximum moment or moment at a given location, or they might just give you the moment and you might not need to draw a shear and moment diagram. But that's where that comes from. It comes from the external applied loads. I is the moment of inertia. Typically on the FE exam, for a mechanics of materials problem, they will either give you the moment of inertia or you are going to have to compute it for a relatively simple cross-section, like a rectangle, a triangle, a circle. You might have a completely separate problem, which is compute the moment of inertia of this composite shape, in which case, okay, that's a little bit more of an involved problem, but that's all they're asking. What is the moment of inertia of this I-beam, right? And that's all they're asking. It's just like a centroid problem, right? Speaking of centroids, we have sigma equals my over I. M's easy, I's easy, but what's y? Y is the distance from the centroid, because when we look at our bending stress profile, we get 0 bending stress at the centroid. The further we get away from the centroid, our bending stresses increase. So if we have a section that is not symmetric, well, we can get a bending stress at the top and a bending stress at the bottom, right? How do we determine those bending stresses at the very, very tippy top or the very, 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 very bottom? M over I times what we call this distance C. This distance C is what's called an extreme fiber distance. The extreme fiber distance is just the distance from the centroid to either the very, very tippy top or the very, 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 very bottom, because those are where the bending stresses are going to be the highest. With me so far? Okay, now, we engineers like things simple, and so sometimes we like to revert things back to a P over A type computation, if you will. We want to take the load, divide it by a number, and get the stress. We want to take the moment, divide it by a number, get the stress, okay? Well, if we have a doubly symmetric cross-section, what we can do is we can recognize if the section's doubly symmetric, then that means the centroid here is going to be right smack dab in the middle, and so this stress and this stress are going to be equal. So what I can do is I can take the moment of inertia, divide it by this distance, and I get a new section property. We have a name for that section property, and we call it the section modulus, right? Remember when you open up your AISC 15th edition steel construction manual and you look at all the properties for I-beams, you have moments of inertia, radii of gyration, remember Z, the plastic section modulus. We haven't talked about that yet, we're going to talk about it later. But then there's this term S. S is the section modulus. So if you want moment over S, that'll give you the bending stress about that given axis. Speaking of, let's look at our final problem that we're going to look at today. And again, like I said, I only wanted to do 3 problems because I don't want to get into information overload land. But let me go back to the notebook here. So here's the problem. I have a beam that is a triangular cross-section. Ooh, that's interesting. It is a simply supported beam. Subjected, we have a 80 Newton per meter load and a 10 meter beam, and we need to determine the maximum compressive bending stress. Okay, maximum compressive bending stress. All right, I'm going to give you a sec to copy this down because I want to make sure that everybody's sort of following along with me on this one. I'll give you a sec. I'll give you a sec. I want to make sure everybody's following with me on this. So while you all are copying this down, I'm going to sort of draw this beam over here again. I'm going to worry about, oh goodness, lost my beam there. I'm going to worry about the units later. We'll convert that here in a little bit. And you'll see why here in a bit. Okay. So we have 80 newtons per meter for a distance of 10 meters. So what is the total amount of load on the beam? So 80 newton per meter per 10 meters is what, 800 newtons? So each reaction is what, 400 newtons? So how do we determine maximum moment? Maybe we ought to draw shear and moment diagrams. Okay. So remember a shear diagram, we start and end at 0, right? So we start, yes.
What does K mean again?
Oh, I'm in US units, that's supposed to be newtons. You're right, that's newtons.
Shouldn't it be? Wait, okay, never mind.
Yeah, I put K for kips.
Well, I mean, I know, but I was converting all my stuff to kilonewtons. That's what you said already.
That's fine. If you want to do that, that's fine. I held off on it, and you'll see why. But either one's fine. I'm using a little bit of my experience to not convert, and you'll see why.
Gotcha.
So, but if you convert correctly, you'll get the same answer. So we start at 0, we jump up 400. What does the shear diagram look like from here to here? Linear. What do we drop down to right here? Negative 400. Okay, what about the area under these triangles? 400 times a half is 200, and 200 times 5 is 1,000. Did I do that right? So this is plus 1,000 minus 1,000. So we start at 0, lot to a little, down to 0, right? So M max is 1,000 Newton meters, but how many kilonewton millimeters is that? See, yeah. So it doesn't matter, all right? May I also remind you of a way to avoid constructing the shear and moment diagram altogether? If I remember correctly, M max for a simply supported beam subjected to a uniformly distributed load is WL squared over 8, right? $80 over 8 is 10 times 100 is 1,000. Right? And y'all know where that WL squared over 8 comes from. It's just a numerical, it's a symbolic integration of this, because this is WL over 2, this is L over 2, so what's the area of this triangle? 1/2 of WL over 2 times L over 2, or WL squared over 8. So that's where that comes from. So. With me so far? So, if sigma my over I, maybe we need the moment of inertia. Pop quiz. What's the moment of inertia of a rectangle? See if you remember. How do you compute the moment of inertia of a rectangle? I'll give you a hint. It's BH cubed over something. 12. There you go. Now, what's the moment of inertia of a triangle? Do you remember that? I don't remember that either, right off the top of my head. So what do I do?
Check the manual.
There you go. You check the reference manual. Now, this is one of those instances where understanding the manual and understanding what's in the manual is important, okay? So this is actually in the statics section. Why is it in the statics section? Well, it's in the statics section because that's where centroids and all that stuff is, okay? So this is where I'm getting this from the manual. This is on page 111. So again, the reference manual is kind of big, okay? And what we've got here is a table showing the moments of inertia of various recognized cross sections. Now, if we look at, let's say, a rectangle, look at what we have here. Okay, now this is really important. Okay, I want to pay attention to this. So I want to show you the rectangle because I want this to make sense. So why is there a BH cubed over 12 and a BH cubed over 3? Why is there a difference? Well, let me zoom in a little further. How about that? What's going on with this notation here versus here? This is the moment of inertia about the x-axis with respect to the centroid. This is the moment of inertia with respect to the x-axis if the x-axis was located at the bottom, right? Because this is the x-axis, that's the y-axis, okay? Whenever we're dealing with bending theory and particularly bending stress formulas are always referenced with respect to the centroid, okay? So what we need is the centroid of a triangle with respect to its centroid, okay? So if we use, and here's the beauty, if you use any of these formulas, what do we see with respect to the centroid? BH cubed over 36, because it's a triangle, it's not a rectangle, so the formula is going to be different. With me so far? So that's what we need. So let's go back to our problem. And if memory serves, we have, what do we have? Yeah. So we have a cross section that looks something like this. Now, what are we going to need for this cross section? Now we know that this is 10 centimeters. We know that this is 10 centimeters. So back to high school geometry. This is an isosceles triangle, right? Okay. We are going to need to know the moment of inertia of this rectangle or this triangle, but we're also going to need to know the location of the centroid, right? Now, what would probably help is understanding what the height is. Here is how we're going to determine the height. I'm going to take this triangle and I'm going to split it in half. And splitting it in half, I'm going to get a triangle look something about like this. This is 10 centimeters, and this dimension is 6 centimeters because I've cut it in half. And so if that's 6 centimeters and that's 10 centimeters, what's the height? 8 centimeters. It's a 3, 4, 5 triangle. So we know that B is 12 centimeters or 120 millimeters, and we know that height is 8 centimeters or 80 millimeters. So what is this dimension right here if this is the centroid? It's a third, right? For a triangle, it's a third. What if you don't remember that? NCES reference manual. So this is going to be h over 3, this dimension, 2h over 3, right? It's h over 3 from the big end. All right? So, what do we need? We need the moment of inertia. Again, it's going to be big. It's a big number because we're taking millimeters to the fourth.
I got 1.37 times 10 to the ninth.
Second.
We got,
Woo, we got some debate.
we got 4.671 times 10 to the sixth.
All right, hold on.
Oh. Yeah. Yeah. I did the 80 to the fourth instead of millimeters.
Okay.
Or whatever. I'll just be a dummy.
Yeah. Okay, I got the same thing. Say it again.
1.71 times 10 to the sixth.
Yeah, that's what I got. Okay. All right. Now, sigma equals my over I. Let's not be robots about this. Let's think about it. What did the problem ask for? Say it. Maximum what? Compressive stress. Now, if I bend that beam like that, is it going to smile at me or is it going to frown at me? It's going to smile. Smiley face, right? So what's experiencing the compression? The top of the beam or the bottom of the beam? The top, right? Now, we know from sigma equals my over I that we have zero stress at the centroid. The further away we get from the centroid, the bigger the stresses are. So the question is, if I go back to my section properties that I have right here, what am I going to use for Y? I need to go from the centroid to the worst case location for compression. Where is the worst case location for compression for this beam? Well, are we saying the end? The top. It's 2h over 3, exactly right. Because that's from the centroid to the very, very tippy top of the beam, right? Does that make sense? Okay, so in this case, Y is 2/3 80, which is what, like 50s, like 53 1/3, is that right?
Yep.
53.33 millimeters. So to summarize, we have M is 100,000, or what was it? Well, how much was M? Well, I said 100,000. I don't think that's right. 1,000. Y is 53.33 millimeters, and I is 1.71 times 10 to the 6 millimeters to the fourth. So if I say sigma is my over I, now just so you're aware, this is a stress, so it is going to be tiny. What do we get? Say it again. Do I have a second?
Yeah.
Now, what are the units? This is a stress, by the way. So it's a kilonewton over a millimeter squared. And the answers are in megapascals. So if I take this and multiply it by 1,000, I get 31 And I think that's that one right there.
I think it's all about units.
I think it's all about units. In all seriousness, this section, the reinforced concrete section, maybe some of the stuff in soils and fluids, units, man, units will mess you up. You know, the concepts are easy. I don't even think the math's all that hard. It's the units. And I have always been a fan, just convert everything to a consistent unit system before you start diving headfirst into the math, because you will find that you will reduce errors at the end of the day. The beauty of engineering is that, yeah, you know, maybe some of the inputs have some wonky units, but we don't really do anything that crazy with them. We take them, we multiply them, we divide them, we get stresses. Stresses are always force per length squared, right? In SI, they're always going to be some form of Pascal or a PSI or a KSI. You're not, you know, if your inputs are all right, the formulas tend to work themselves out in terms of units, you know. All right. Now, let's talk about the next review session, then I'll let you go. So whenever I teach deformables, there are what I call the big four stress formulas. And that is axial, torsion, bending, and shear, the shear stress formula. I'm going to hold off on doing the shear stress formula because I think that I don't want to dip into information overload. So I want to talk about the bending or the shear stress formula on Thursday. I also want to talk about Mohr circle, because I think that does not get enough love. I don't think it's that hard either. And then if we have time, we'll talk about buckling. And that is a crash course in mechanics and materials. Any questions? Any thoughts? Well, I'm glad you came. And I'm going to go ahead and stop the recording. Yes?
I just wanted to ask about the first problem. I didn't know that.
Oh, hold on.
It said that it was uniformly loaded.
Yes.
So if that wasn't assumed, would that mean you can only like calculate a stress at like specific infinitesimal spots?
No. Typically what that means is that the load is going through the centroid. And if the load is going through the centroid, that means that there is no bending. So you don't have axial stress and bending stress. So, for example, if I sit right on the centroid, I'm not causing any axial load to the system. But the moment I move, now there's load and eccentricity, which can cause bending. So yeah, that's kind of what that means. Yeah, no, that's a very good question.
So in the reference manual for the last problem, for the moment of inertia of the triangle, that's actually given as I, XC.
Mm-hmm. And any time that you are using, or that you are trying to determine bending stresses, all of the bending stress formulas, sigma equals my over I, the y is measured from the centroid. You see what I mean? Because here's the thing, if you're bending, think the bending theory has to reference the centroid, right? Because if you have a bridge beam supporting load, the beam doesn't care where the axis is. Do you know what I mean? Like, it's just a load on a beam. The beam's going to respond the way it's going to respond. The reason for the centroid is because it is the only point that I can determine on any beam. You know what I mean? It is a common frame of reference for all cross sections, right? And it has mechanical relevance because there's zero bending stress and strain at the centroid. So. Sound good? Well, that's all I have for you. We will pick this up again on Thursday. I know.